And I'll be celebrity teaching your lesson on linear and angular speed today. So this is from chapter 4, section 2. And linear and angular speed is really in regards to analyzing circular motion. So we're talking about how many times are we traveling around a circle. So the formula you just learned for arc length can be used to calculate something called a linear speed. So linear speed is measured in units of length per time, so something like miles per hour. You can also use the speed that an object is going around a circle to calculate its angular speed, and that is measured in units of angle rotation per amount of time, so something like radians per minute or degrees per second. So those are the two things that we're going to be discussing today. And you may want to highlight those things. Linear speed is how fast an object is moving around a circular path. And then you have your angular speed is the rate that the object is rotating around a fixed point or the center. Excuse me. Okay, so let's say that an object is moving around a circle at a constant speed, and the radius of that circle is r. So we know that s, which is the arc length, if that is the length traveled by the object during an amount of time, t, then we can calculate the object's linear speed by dividing the arc length by the amount of time. So we use the letter v to represent linear speed, v for velocity, this is kind of another word for speed. And then to calculate the angular speed, you would take the angle of rotation, so how many radians has it rotated, and divide that by the amount of time that's passed. So theta divided by time would equal the angular speed. And we use the Greek letter omega to denote angular speed. So here are your two formulas. Let me try that again. We'll discuss them again on the next slide. So feel free to pause this video and write down your formulas anytime you need to. So linear speed, again, we use the letter v, which is like velocity. V equals arc length divided by time. And the angular speed, we use the Greek letter omega, and that is just the angle divided by the time. The angle being represented by theta. So again, feel free to pause this and write your formulas down. So these problems can be a little bit tricky. So what I recommend is that you think about these two types of speeds in terms of how many times is your object going around the circle. In other words, how many revolutions. So one revolution is one time around a complete circle. And how long does it take for the object to make one revolution? So if we're thinking about angular speed, one revolution would equal 2 pi radians. Of course, one revolution also equals 360 degrees, but for pre-cal, we're going to stick with radians. If you were thinking about linear speed, one revolution would just be the length of the circumference, right? So we know to calculate the circumference, c equals 2 pi r. You would need the length of the radius, and you multiply that by 2 pi, and then that would give you the circumference of the circle. That would also tell you the length of one revolution. So kind of just to keep track, we're doing 2 pi radians for angular speed, and then we're just simply using the circumference for linear speed. Remember, the circumference is also an arc length. It's just the length of one full rotation. So when you're working these problems, it also helps to use dimensional analysis like we do in science. So let's say you're trying to find the angular speed of an object that is going around the circle 3 times in 1 minute. So 3 revolutions per minute. Of course, we know in one revolution, it is passing 2 pi radians. So we can just multiply 2 pi radians in each revolution times 3 revolutions per minute. And then the revolutions would cancel each other out, and you're left with a unit of radians per minute. Of course, 3 times 2 pi is 6 pi, and then this gives us a unit of angular speed. So that would be our omega. All right, let's try some examples. So example 1, we have the tire of a bicycle is rotating at a rate of 140 revolutions per minute. So get that in your head what that means. In 1 minute, the tire rotates 140 times. Okay, so remember that we have angular, maybe, angular speed and linear speed. Okay, so for angular speed, 1 revolution equals 2 pi radians. And for linear speed, 1 revolution equals the circumference of the circle. And circumference is just 2 pi r. Okay, so for part A, we want to find the angular speed of this tire in radians per minute. You also want to pay attention to your units. If you are using the same unit of time, you don't have to convert that. If not, then you'll have to go back and convert that later. But these revolutions are in minutes, and then it's asking for angular speed in minutes. Later, it's asking us for linear speed also in minutes, so we don't have to worry about converting any of that. So angular speed, omega, equals the number of radians traveled per amount of time. Okay, again, our time, we're using minutes. So we're going around the circle 140 times, right? Each time we go around the circle, how many radians pass by? How many radians are in one full circle? You guys know now that there are 2 pi radians in one circle. So we can multiply 2 pi radians in one full circle, or in each revolution, times, we're going around the circle 140 times. I don't like that. Ugly. Go back. 100. No. My B, guys. 140 revolutions per minute. That's the rate. And notice the revolutions cancel each other out. 140 times 2 is 280 pi. And the units left over is in radian per minute, which is what we want. Radians per minute is my unit of time for angular speed. So in each minute, we are completing 280 pi radians. All right, part B is asking us if the radius of the bicycle is 15 inches, find the linear speed in inches per minute. So linear speed is represented by V, and that's just the arc length divided by the time. In this case, the length of the arc, we're going to use the circumference, but since we're going around the circle 140 times per minute, that means in 1 minute, we have 140 circumferences that we're going around. So first, let's calculate the circumference. 2 pi r is 15 inches. So that's going to equal 30 pi inches. Okay, so that is representing my S. And then time is just in minutes. So that's just going to be the same. So again, we're traveling around the circle 140 times each minute. The circumference of the circle is 30 pi. So in 1 revolution, we travel 30 pi inches. Cancel your revolutions. 140 times 30 pi is 4,200 pi. and that is in inches per minute, which is what the problem calls for. So there you go. Okay, moving on to example 2. Find the rotation in revolutions per minute given an angular speed of omega equals 6 pi radians per second. So here we're kind of working backward. So wrap your brain around what this is giving you and what it's looking for. So you're told this object is rotating at an angular speed of 6 pi radians per second. Each second, the object covers 6 pi. So think about that. How many radians are in one circle? 2 pi. So how many circles do we have to go around to get to 6 pi? Again, you know that one revolution equals 2 pi radians. So that's pretty easy math. We know that if we have 6 pi, we're going around our circle 3 times. 2 pi, 2 pi, 2 pi. So omega, which is arc length over time, equals 6 pi radians per second. All right, so we need our, if we want to calculate our number of revolutions, we would just take that speed of 6 pi radians per second. We divide that by the number of radians in each revolution. Okay, so then the radians cancel out, and this means that we are going around the circle 3 times. Sorry, bear with me. We're going around the circle 3 times in 1 second. Okay, pay attention to the question though. It's asking us for revolutions per minute, so we just need to use our dimensional analysis and convert this into revolutions per minute. So I need to know how many seconds are in 1 minute, and of course there are 60 seconds per minute, so then the seconds cancel out, and we have, actually move this here, 180 revolutions per minute. That is what that is asking for. Again, this speed, you're talking about how many times are we going around the circle? How many radians are we covering, or how much length are we covering as we rotate around this circle? Okay, example 3. Find the radius given a linear speed of v equals 20 inches per second, and the rate of rotation is 8 revolutions per minute. Okay, so we're working backward here to calculate the radius given the linear speed and the rate of rotation. So in 1 minute, we're going around the circle 8 times, 8 revolutions per minute. But in order to find the radius, we need more information. So they give us the linear speed, which is 20 inches per second. Now notice those units are different. We have minutes and seconds. So we will have to convert our time at some point here. Okay, in 1 minute, we're going around the circle 8 times. We are also traveling 20 inches per second. So remember that linear speed is just arc length divided by time. So if you want to calculate your arc length, you would multiply your speed times your time. Okay, that makes sense. Angular speed is your angle of rotation over time. If you wanted to calculate your angle of rotation, you just multiply your angular speed by the time. Hopefully that makes sense to you guys. Okay, and then the formula that you used, that you just learned for arc length, is S equals R theta, right? So if we want to calculate the radius, or r right here, we just need to know the length that we're traveling in this amount of time and the angle of rotation we're traveling in this amount of time. So we need s and we need theta here. So we can use this linear speed to calculate the arc length, and we can use this rate of rotation to calculate the angle of rotation. Okay, so we have v equals 20 inches per second. We need to convert that into minutes so that we're using the same unit of time. So I'm going to multiply that by 60 seconds per minute. Cancel my seconds. So this is traveling 1,200 inches per minute. Okay, so now we're in the same unit of time. It's a little bit easier to compare all of these speeds with each other. Okay, omega, we're going around the circle 8 times in 1 minute. And each time around the circle, we travel how many radians? 2 pi radians per revolution. So we can cancel that. And my angular speed is going to be 16 pi radians per minute. Okay. Now, for both of these are per 1 minute. So up here, if my time is 1 minute and I multiply the 1 times the speeds, that means that S is just 1,200 inches and theta is just 16 pi radians. All right, so we have what we need right here to calculate the radius. If S equals r theta, then I have 1,200 equals r times 16. It's really hard to write with one of these styluses, so thank you for being patient with me. We're going to divide both sides by 16 pi. And that means that r, and we're going to round this to the nearest tenth, so 1,200 divided by 16 pi is approximately 23.9 inches. There you go. And of course, you can check your answer by working it forward to make sure you get the same linear speed. Okay, so this last one is just kind of for fun to think about it. You know that a clock has 3 hands on it. You have the hour hand and the minute hand and the second hand. So this thought question is, which of the 3 hands has the fastest angular speed and why? So you can probably just look at a clock and tell me which one goes the fastest. Obviously, the second hand goes the fastest, right? But using what we've talked about with angular speed, how can you prove it mathematically that the second hand is the one that travels the fastest? Well, just think about it in revolutions per amount of time, right? So the hour hand travels how fast? How long does it take to go 1 revolution? So it takes the hour hand to go all the way around the whole circle. It takes it 12 hours, right? The minute hand How long does it take to go around the circle one time? It only takes 1 hour to travel all the way around the circle. The second hand, it goes around the whole circle in how long? Well, it only takes a minute for the second hand to travel around the circle. So since these are different lengths of units of time, we want to convert those so that we can compare them. We'll do this in terms of hour. So the minute hand is traveling 1 revolution per hour, right? The hour hand is traveling 1 revolution per 12 hours. So that is 1/12 of a revolution each hour. And the second hand is going around the circle in a minute. And we know that there are 60 minutes in an hour. So we multiply that times 60. And the second hand is going 60 revolutions in 1 hour. So we can see that that one is significantly faster than the other two. Okay, and then the next thought question is, if your minute hand right here is 4 inches long, how fast is the linear speed of this tip of the minute hand right there? How fast is it going around the circle? So this one I'm looking for the linear speed, where V equals S over T. So we need the circumference of the circle. Circumference is going to be 2 pi times the radius is 4. That equals 8 pi inches. Okay. The minute hand goes around the circle once per hour. So V would equal 1 revolution would be 8 pi inches per hour. And that is approximately equal to 25.13 inches per hour. So just kind of something fun to think about with the clock. And that is the end of linear and angular speed. So now you can try the problems on your Intro to Trig worksheet. Thank you guys for listening.